Welcome to this course on nanostructured materials, synthesis, properties, self-assembly and applications. We are in the module 4 of this course, and in this module 4, which has 12 lectures, today we have the 8th lecture in that series of 12 lectures, and we are discussing magnetic properties of nanostructured materials. And we looked at the basic magnetic properties of materials in general in the first lecture of these 3 lecture series regarding magnetic properties, and then we looked at what happens to the magnetic properties in nanostructured materials. That was in the last lecture, which was lecture 7, and we will continue on that. We about the applications of these magnetic nanoparticles in different devices and in biotechnology. And what we learned so far are some very important features which in the magnetization which change as the size of the particle becomes small. So, the most important point was the concept of superparamagnetism. When a particle becomes small, if it is a ferromagnetic, you would expect that the magnetization increases as you decrease the temperature and will suddenly increase to a large extent below a certain temperature, which is called the Curie temperature. This should be the behavior of a normal ferromagnet. However, when such a ferromagnet or a magnetic substance, commonly most of the magnetic substance we normally refer are ferromagnetic substances. So, when we say that they in a ferromagnet, they are basically talking of something which normally people call as magnets or permanent magnets. Now, these materials should show a Curie temperature below which the magnetization or the magnetic susceptibility should shoot up. That means, it should increase at a much faster rate below that temperature, compared to the rate at which it was increasing below that above that temperature when it is a paramagnet. So, the paramagnetic to a ferromagnetic transition occurs at a temperature T c, which is called the Curie temperature. This should happen in a normal magnetic material. When you decrease the size of the particle in the nano dimensions, what is seen that instead of this large change in the magnetization below T c, the magnetization starts to decrease. Now, this is called the blocking temperature, and that is the reason we have what is called a super paramagnet. It tries to behave like a super paramagnet instead of a ferromagnet. So, this we discussed in our previous lecture about super paramagnetism, about blocking temperature, and how this difference is present in nanoparticles of different materials. So, today let us talk about some real nanoparticles which show different magnetic properties, especially in magnetic oxides and their applications. So, this is an example of magnetic properties of metal oxide nanoparticles. So, when we say metal oxide, it can be a binary oxide, say copper oxide or nickel oxide, or say cobalt oxide. Of course, it cannot be zinc oxide, because it should have some magnetism, and normally zinc oxide is not magnetic, because it does not have an empty d orbitals. So, normally when we talk of metal oxides, we tend to talk about transition metal oxides, and transition metal oxides like nickel oxide, cobalt oxide have very rich magnetic properties. Now, here we discuss how we are going to make these metal oxide nanoparticles, and one of the methods which has been used to a large extent is to first make transition metal oxalates and their nanostructure. So, many reports are there where nano rods of transition metal oxalates has been made using microemulsions. Microemulsions we have discussed earlier, and basically this is a methodology by which a large amount, many types of nanomaterials can be made and their size and shape can be controlled. So, in this case we are talking of metal oxalate nanostructures having anisotropic structures like rods. So, using microemulsions we can make this kind of rod shaped structures of transition metal oxalates. So, say you have copper oxalate, and if you use a temperature say 400 to 500 degree centigrade, these rods of copper oxalate or nickel oxalate decompose to give you particles which mainly are spheres, but sometimes under different conditions you can also get other type of structures like cubes etcetera. So, of oxides. So, here you have oxalates, you decompose at heat them at high temperature say around 400 to 500 degree centigrade, and you get oxides, and the size of these particles are in nano dimensions. So, they can be 20 nanometer, 50 nanometers, 100 nanometers depending on what was the type of metal oxalate you chose and how was the metal oxalate prepared using which microemulsion. So, that controls the shape of the starting metal oxide, and that when you decompose controls the shape of the final transition metal oxide nanoparticles. So, here you can make MnO. If you start from manganese oxalate, you will get manganese oxide. You can get nickel oxide if you start from nickel oxalate, you will get copper oxide if you start from copper oxalate. So, you can get nano sized metal oxides, and you can study the magnetic properties of these metal oxide particles, and you can control the size of the particles by controlling the microemulsions. For example, if you use a solvent like isooctane, when you synthesize this copper oxalate to get finally copper oxide, then you get particles of size 25 nanometers. However, if you make copper oxalate using normal octane instead of isooctane, they are two different isomers, then in that case the copper oxide which you get has particles with size of approximately 80 nanometers. So, depending on the methodology, whether you take in the microemulsion isooctane or normal octane, you can get the resultant oxalates of different size and shape, and you will ultimately on decomposition get different sized particles of copper oxide. This is an example that we discussed of copper oxide, but the same can be discussed about manganese oxide or nickel oxide or say ruthenium oxide or any other oxide, and how the starting material, starting solvent and surfactant etcetera will affect the transition metal oxalate, and that in turn will affect the size and shape of the transition metal oxide. So, this is a big area of research and lot of work has been done and lot is known about how to control the size and shape of the final metal oxide particles which are magnetic in nature. So, now let us look at their magnetic properties. So, this is an example of copper oxalate. It crystallizes as hydrate. So, the actual formula is given here. 1 copper is to 1 oxalate ion and 1 mole of water is hydrated, and you can find out using X-ray diffraction etcetera the structure, and this is transmission electron micrograph showing you the rod like structures using isooctane to make the microemulsion initially, and in this case you have used normal octane to make the microemulsion, and you see the rods are of different shape size compared to the rods obtained here. So, these are both are copper oxalate, both will have the same X-ray diffraction pattern, but both have different morphology because of change in solvent. Now, when you decompose this rods of copper oxalate to form copper oxide, they give you particles of size 25 to 30 nanometers. And when you decompose these rods at around 450 degree centigrade, you get copper oxide which has size of 80 to 90 nanometers. And when you now study the magnetic properties, because that is the point which we are discussing in this lecture, that how does the magnetic properties change with the size of the particles. So, when you look at the magnetic properties, what you see that the magnetization as a function of temperature in this particular copper oxide, there is a slight change around 80 degrees K, 80 Kelvin. Okay. Whereas, in this copper oxide, both are copper oxide, from the X-ray you can make out. In this copper oxide, there is a change in the magnetization. So, this axis is magnetization, there is an increase in the magnetization at around 200 210 degree Kelvin. So, both these particles show some kind of a weak ferromagnetism, because whatever was the magnetization earlier, now the magnetization is increasing. So, this sudden increase in magnetization is actually ferromagnetism if it is very sharp. That is most commonly the reason why the magnetization should increase. Since the increase is not as sharp as a normal ferromagnet, hence we sometimes call this as weak ferromagnetism. But more important is the fact that because of different size of particles, here you have 25 to 30 nanometers, and in this copper oxide the size of particles is 80 or 90 nanometers. The two different particles size gives you two different TCs. The weak ferromagnetism, the temperature at which that occurs is called the Curie temperature, and that is around 210 Kelvin here, and in this case it is around 80 Kelvin. What is of more importance is that if you take bulk copper oxide, where the size of the particles is much larger, say around 1 micron or 2 micron, and if you measure the magnetization of that copper oxide nanoparticles, then you will get a totally different behavior, because copper oxide bulk or large size particles do not show ferromagnetism. It is weak, it is an antiferromagnet around 230 Kelvin. So, it shows a totally different behavior, and hence this is a very important characteristic of nanoparticles, that it shows magnetic properties very different from particles of larger size, but of the same material. And this particular thing, many times it is called reversal of magnetization, that is something which is antiferromagnetic shows weak ferromagnetism, something which is ferromagnetic shows something like superparamagnetism or weak antiferromagnetism. Now, in some cases it is called reversal of magnetization, and the reason is this, that when a large particle is becoming smaller, then even if the dipoles in the bulk in the large particle can be organized, the dipoles on the surface remain disordered. And so, in the large particle, the core of the particle is ordered and contributes to the magnetization. However, when you make small particles, there is hardly any core and everything is on the surface, and so you do not get a net magnetization in that case, and so a ferromagnetic substance tends to become weakly antiferromagnetic or behave as a superparamagnetic. Now, so there are reasons why this transformation occurs in different cases, and one can study them in detail, and lot of work has been done in understanding the magnetic properties of bulk materials transforming to nanoparticles. So, this is one of the reasons weak ferromagnetism is seen in copper oxide nanoparticles due to uncompensated spins. That is, the spins which are on the surface in copper oxide can give rise to weak ferromagnetism, although ideally in the bulk copper oxide should have the magnetic moments should be aligned opposite to each other, giving it net antiferromagnetism for a large size copper oxide particles. But in this particular case, since you will have lot of dipoles on the surface, that large magnetic moments which are supposed to be aligned opposite to each other gets distorted, and you have only surface magnetic moments to contribute, and there can be weak ferromagnetism due to uncompensated spins on the surface. So, all the spins may not get compensated, which should be in an ideal antiferromagnet. So, nano copper oxide particles can get attracted to a magnet, whereas bulk copper oxide will not get attracted to a magnet, because that is a true antiferromagnet. So, hence such materials can be put into devices as a magnetic sensor, and you can switch on and switch off the magnetization depending on this kind of materials. So, it can be used as a magnetic sensor. Now, you can look at other materials of similar kind. For example, instead of copper oxalate, you can look at nickel oxalate nanorods, which are shown here, and again the diameter and the length can be changed by changing the starting solvent. Here it is isooctane and here it is normal hexane, and you see these are much narrower rods, thinner 250 nanometer diameter. Here they are broader 500 nanometer diameter, and these rods also decompose at around 450 500 to give you the oxide, which is nickel oxide. And when you look at the magnetic property of this nickel oxide, say the magnetic susceptibility as a function of temperature, then you calculate the magnetic moment. It is 3 times larger than the magnetic moment of true bulk nickel oxide, because nickel oxide is again antiferromagnetic, and so the magnetic moment is very low in bulk nickel oxide. That means, nickel oxide having large particles, micron sized particles, they have a large moment, they have a small moment because it is antiferromagnetic. And when you make it nanoparticles, the size becomes very small, there is uncompensated spin on the surface, and or you can say surface spins dominate, and the magnetic moment will become much larger compared to a nickel oxide particle, where all the moments get cancelled, because most of the moments are in the bulk, and the bulk moments get cancelled because it is an antiferromagnet. And so, when you measure for a nanoparticle of nickel oxide, you see that the magnetic moment is 3 times larger than the particles of a bulk nickel oxide. So, it can be magnetic moment, which also means if when you measure susceptibility, the values are much larger than the susceptibility of bulk nickel oxide. So, we looked at copper oxide, nickel oxide. Similarly, you can make many such magnetic materials, and many of these nanomagnets have applications if you can order them properly. So, if you can order these nanoparticles, then it will have a tremendous role in applications. So, self assembly of pattern nanomagnets is something one strives to obtain, so that we can make use of these nanoparticles. So, here is a template mediated self assembly of nanomagnets. We are calling these particles as nanomagnets, and you can see that they are organized very orderly manner, and this is a technique by which you are observing these particles is called MFM, that is magnetic force microscopy. It is a derivative of the atomic force microscopy. Of course, you can do both atomic force microscopy and magnetic force microscopy on the same material using different probes on the using the same piezo on which you can move the scanner. Now, on the left is MFM, which is the magnetic force microscopy. On the right is the AFM, which is the atomic force microscopy. In the AFM, you see pictures or an image which is generated by the variation of the force which the cantilever is feeling when the cantilever is moving across the surface of this material, and wherever it has different types of forces, you see these different colors from dark brown to light brown, etc. So, it basically maps the force at different points of the sample, and this force is related to the atoms which are present, and accordingly you will have a idea of the where the atoms are positioned. However, the MFM maps the magnetic field which is coming out, or the magnetic moment from each position, the magnetic force you can call it. So, ultimately what you are measuring is some magnetic property of the material. So, if the magnetic property is same everywhere, then you will just get one same shade of color to be imaged. However, if it is varying, for example, this point has a different magnetic force compared to the point in between these two light brown colors, there is a dark brown region. So, that dark brown region has a different magnetic force than these light brown regions, and both these light brown regions or yellowish regions has similar kind of magnetic force. So, then when you image the whole thing, you get an idea of where the nanomagnets are. Similar particles having similar magnetization will show you similar type of features. If you have particles which have a larger magnetic force, will show up as a different feature. So, using that you can map the whole surface as a function of the magnetic force. That is why this is called an image generated by magnetic force microscopy. Now, in this particular case, each of these is a iron platinum nanoparticle or dot, we are calling from the term quantum dot, which is normally used in the optical sense, where you have particles which show quantization, and in the optical frequencies they have particular absorption in the visible, and here these can be called as magnetic dots, because each particle has some magnetization, and hence in general these are made up of iron platinum. Iron platinum in the bulk is a hard magnet, it is a magnetic substance, has a high magnetization, a high remanence or remanent magnetization, has a high coercive field, and that is why it is a strong magnet or a hard magnet. And iron platinum, small sized iron platinum or nano sized iron platinum, when you make a surface out of it with small particles of this material, you have a pattern of nanomagnets. So, that is what you are discussing here, a self assembly of pattern nanomagnets, and you have this can be prepared using a template mediated method, and it has high potential for many applications, because these are normally used for magnetic recording, etc. So, this high density, that means many particles over a square unit area are required, then only you will have high density magnetic recording or other nanoscale devices used for magnetic recording. Then let us look at what we discussed so far is two, 3 examples of magnetic particles, and we mainly discussed the synthesis of magnetic oxide particles using oxalate and its decomposition to give you a magnetic oxide, and then look at the magnetic properties of that magnetic oxide nanoparticles, and we see that it is different from the bulk particles of the same material. and it shows up in the magnetization studies, and typically when you are expecting something to be antiferromagnetic in the bulk, it tends to become weakly ferromagnetic, and when something is is ferromagnetic, can become super paramagnetic at small size. Now, when you decompose this oxalate to become small sized metal oxide particles, one can study this kinetics, and that has been done. This is an example of decomposition of cobalt oxalate to cobalt oxide, and now note that this is a formula which is not like manganese oxide, which we study MnO, or nickel oxide NiO. This is CO3O4, and this is a very important magnetic material, and cobalt oxide can have different formula. You can have cobalt oxide with 1 cobalt and 1 oxygen, you can have cobalt oxide with 2 cobalt and 3 oxygens, and you can have this cobalt oxide with 3 cobalts and 4 oxygens. Now, you can study the change from oxalate to oxide using different kinetic parameters and see how the shape of the particles get affected, and you can also see how the length of the rods get affected, and instead of spheres can you get some other kind of assemblies, because earlier we showed that you get rods of the oxalate and particles, spherical particles for nickel oxide or copper oxide. Here we will see that you can get different types of particles for cobalt oxide by varying the temperature, etc. So, you see that when you heat at 600 degrees cobalt oxalate, you get cobalt oxide of this kind, where you can see these particles, small particles are forming a chain, and the dimension of these particles are around you see 95 nanometers is the around the diameter, and the rod length is around 600 nanometers. So, this is if you decompose at 600. If you decompose at 450, then you get different types. The much smaller 80 nanometer is the dia, and the rods are around 800 nanometers. Each particle in this is around 30 to 40 nanometers at 450 degrees. So, whereas at 600 degrees the particles appear to be larger. If you decrease this heating temperature to say 300 degrees, you still get rods, but these rods are made up of small particles, and these small particles are around 5 to 10 nanometers. So, what this study shows is that using different temperatures, etc., you can get the same cobalt oxide in different morphology, and the size of the particles which form this anisotropic rod like structure, this size, the small size can be varied from 5 nanometers to around 80-90 nanometers. So, you have a wide variation of the size depending on the conditions that you are using to make these particles. So, this can be plotted here, and you can see the aspect ratio goes down with temperature, increase in temperature. The aspect ratio is the ratio of the length and breadth, and you can see that if you divide the length by the width, it is like 10 when you heat at 300, whereas the ratio becomes around 7 when you heat at 600. So, aspect ratio changes, the rod length changes, the rod length is decreasing, the rod diameter increases. So, what is happening is the length of the rod decreases, the rod diameter is increasing, and the rod length is decreasing. That is why the aspect ratio is decreasing. So, these effects can be done and vary the cobalt oxide, and all these cobalt oxide particles are magnetic. The bulk particles are also magnetic, the micron sized particles are also magnetic, and these particles which are aligned to form this kind of rod shaped structures, if you measure their magnetization or susceptibility, this is molar susceptibility on the y axis, you see chi subscript m, capital M. So, capital M is for molar susceptibility, that means what is the susceptibility, magnetic susceptibility for 1 mole of this substance. So, it is units are EMU per mole, which is electromagnetic units per mole, and here you have temperature, and you see that as you cool, like any paramagnet, the susceptibility will increase as you cool with temperature, or magnetization will increase as you cool with temperature, but at a particular temperature which is the nil temperature, you start a decrease in the magnetization or the susceptibility, and this temperature is called the nil temperature, because cobalt oxide is known to be an antiferromagnetic substance, and in all antiferromagnetic substances the transition temperature from the paramagnetic to the antiferromagnetic state, this temperature is called the nil temperature, and that is for this 35 nanometer sized particles, this nil temperature that we get is around 35 Kelvin. So, it is around 35 Kelvin that this transition occurs, and the bulk the effective moment is around 4.9 Bohr magnetons, which tells you that it should have around 4 unpaired electrons, right. And if you have bulk CO3O4, then bulk CO3O4 should have a nil temperature of around 40 Kelvin. So, if you have micron sized particles, the nil temperature is higher, and when you have smaller sized particles, the nil temperature gets lowered, and actually it can change over to weak ferromagnetism like you saw in copper oxide. In this particular case, the antiferromagnetism of bulk or large particles of cobalt 3 oxygen 4 is seen, but the temperature at which the antiferromagnetism is seen is lower than what you will see in the bulk. Okay. So, it is 35 Kelvin in this case in the nanoparticles, and it is 40 Kelvin in micron sized particle. And so, if you plot size of the particles, so the average size or diameter of the particle, if you plot along with the decomposition temperature, you will see that as you increase the decomposition temperature from 300 to 600, the average size of the particle is increasing. Not only that, the nil temperature is also increasing. So, what we showed for was 35 nanometer particle shows a nil temperature of around 35. This is nil temperature on this axis, whereas if you decrease the size of the particle to say around 7-8 nanometers, then the nil temperature goes down to 31 Kelvin. Note that the micron sized particles have a nil temperature somewhere up there. So, it is around 40 Kelvin for micron sized particles, much larger, and for nanoparticles, as you are decreasing the size of the particle, the nil temperature is decreasing. The decrease is gradual, because from 35 Kelvin it goes to 31 Kelvin when the size of the particle is decreased from 35 nanometers to around 7 nanometers. So, that is the change in the nil temperature with particle size. So, these are very important, that means you can control the size of the particle and you can control the magnetization of the particle. So, that is the connect that you want. So, you have a handle on a material now no more has a standard nil temperature. So, earlier if you look at a book, iron oxide has a nil temperature of x, that is fixed, but now you cannot say that iron oxide will have a temperature not nil temperature, it is a Curie temperature of some number, and that number need not be fixed, because it will depend on the size of the particle of iron oxide. So, you will now have many numbers, many Curie temperatures for the same material which is ferromagnetic, and many nil temperatures for the same material which is antiferromagnetic. So, so you will not have a fixed number, because the number will change with the change in the size of the particle. Now, there are many applications of magnetic nanoparticles, and these are some of the applications of magnetic nanoparticles which are listed here. So, you can use them as MRI contrast agents. I think we mentioned yesterday in the last lecture that you can use for medical resonance imaging. So, MRI stands for magnetic resonance imaging, which is also called medical imaging, because you image a part of the body or the brain using a source of a magnetic field, and at the same time you have to do some other aspects, either depending on whether you are doing spectroscopy or imaging. But main thing is you are trying to map the magnetic field inside some organ or inside the brain, and the magnetic field has to be picked up by some sensor or some detector. Now, these contrast agents, when you add them, they help you in identifying the magnetization of a particular place. So, if you use a contrast agent and it goes to particular cells in the kidney, then you can see those cells much better against the background of all the other things which are there. So, MRI contrast agents help you see the part of the cell or body which you, organ where you are interested. So, suppose you want to see a tumor very well and you are going to use medical imaging technique, your MRI contrast agent, if it goes to those tumor cells, then you can locate them much better. Okay. So, that is the use of MRI contrast agents. They are also used for magnetic hyperthermia agents. That means, suppose you put these magnetic materials. Now, these magnetic materials, because of the hysteresis loop, if you apply a magnetic field, then you can have some kind of heating. So, hyperthermia means you can heat the environment with magnetic particles when you apply a magnetic field. So, suppose there are tumor cells and you want to break those tumor cells. So, many times you can heat them and destroy them. Now, if you can send these magnetic particles exactly to the cell which you want to destroy, then once these particles go inside those cells and you apply a magnetic field, these particles will then dissipate energy. When it dissipates energy, it will heat up the neighborhood, and the cells which are nearby will get destroyed, because most of the cells get destroyed above a temperature where the proteins get denatured. So, around 70 to 90 degrees, most of the proteins get denatured, except some very rare proteins which do not get denatured. Once the proteins get denatured, they cannot function, and so the cells will die. So, what you want is, by hyperthermia, magnetic hyperthermia means you are heating through magnetic fields. You apply magnetic field and the magnetic particles then will dissipate energy in the form of heat through this hysteresis loop. You can calculate how much heat it can do. Then the third important thing is magnetic data storage, which is a very important part of our day to day life. So, other than the magnetic hyperthermia agents, data storage is very important. Most of the hard disks that you use, your CDs, hard disk, your pen drives, they are all data storage devices, and most of them use magnetic methods for data storage, and in those places you can enhance the ability of data storage by using magnetic nanoparticles. Apart from that, you can have magnetic separation, especially in water treatment, where you can have waste materials tagged to magnetic particles, and then you apply a magnet and remove the particles. So, the waste will come along with the magnetic particles and can be removed with the help of a magnet. Finally, you can do in vivo detection of biological targets using magnetic fields. So, the MRI contrast agents, as I just mentioned, there can be different types of contrast agents. you can use what are called paramagnetic contrast agents. These paramagnetic contrast agents are also called T1 type agents. The term T1 comes from what is called relaxation time. It is from NMR spectroscopy, which has got two types of relaxations. One is the spin lattice relaxation and the other is the spin relaxation. So, the T1 is the spin lattice relaxation, and these paramagnetic contrast agents are normally some gadolinium type of compounds, chelate compounds, that means gadolinium complexes, and gadolinium has free electrons in its F shell, and those electrons give it the paramagnetism, and these gadolinium compounds are used as paramagnetic contrast agents and are also called the T1 agents, because the spin lattice relaxation time is affected. Whereas, the magnetic nanoparticles we are talking about or are interested are like the super paramagnetic iron oxide, which is called SPIO, which means super paramagnetism is the property which we are going to use in this contrast agent. And these iron oxide nanoparticles, they are also biocompatible, that is why they can be injected in the body, are used for MRI contrast agents, and these particles have a size between 3 to 10 nanometers, and these small sized iron oxide nanoparticles which are T2 agents, that means they affect the spin relaxation time. It decreases the relaxation time actually, and that brings about a contrast when the magnetization is being recorded. So, like when you take a photograph, you record a picture. When you do a MRI or any medical imaging, you record a picture, but the picture is dependent on the magnetization of the object which it is trying to form an image. So, wherever the magnetization is different, it will have a different contrast, and these super paramagnetic iron oxide particles help increase the contrast, and so it helps you to see that position much better in the background because of the excess contrast. So, for example, you see on the left side you have there is water here, and you apply a magnetic field, and the water molecules are shown here, and the contrast, the magnetic resonance should create a contrast, but you do not see a much contrast here. Okay. Whereas, the same solution if you add in the water some magnetic nanocrystal. So, this is a magnetic nanocrystal, these green ones are magnetic nanocrystals, and so there will be a magnetic field associated with this magnetic particle, which will give you a net magnetic moment like shown by this arrow inside the particle. And in the presence of the external magnetic field, it will align in that direction, and it will induce this field around this. So, you had a magnetic field due to the external field which you applied, which was M in this case. In this case, you will have the magnetic field M plus the additional field created by these magnetic nanoparticles. So, the total field will be M plus some delta M. Okay. So, the enhanced magnetic field will cause an enhanced contrast, and you will see much darker MRI pattern. So, wherever you have these magnetic particles, you will have much more contrast, and that is why they are called MRI contrast agents, and they are used extensively in medical imaging. So, this is what we discussed, that the particles induce magnetic spin and perturb the nuclear spin relaxation process of the protons of water, and the T2, the spin relaxation time of the proton decreases due to inhomogeneity in the local magnetic field and the fluctuating magnetic fields at molecular level, and the images become much dark, and this is called as negative contrast agent. You can also have positive contrast agent, where this images will become light. So, here the image is the wherever the particle is becoming darker. So, basically what you are doing by adding the particle is you are affecting the spin relaxation time of the protons of the water molecule, because this is in solution. So, water is there and the protons of the water will always have a signal, magnetic signal, and the magnetic field which is being created by this contrast agent, by the nanoparticles, will affect the spin relaxation time of the protons of the water molecules. And when it affects that you can see by an enhanced contrast in the MR images. So, this is the role of the nanoparticles as an MRI contrast agent. This is an example where the super paramagnetic iron oxide particles have been coated with some dextran or something you can coat, because normally it is not given directly the nanoparticles inside the body, it is coated with something, so that it goes only where you want it to go, otherwise it will react at all places before it reaches the final destination. So, here it is coated with dextran and are sequestered by phagocytic Kupffer cells. You see in the liver, we want to target these particles to go to the liver, because you want to image the liver, and in this case you see the contrast is weak, there are no particles in this case, but when you give the particles in the liver, the contrast is enhanced, and you can see that this particle, this is the tumor here, that is what they are trying to say, and this picture is in presence of the nanoparticles. So, the contrast is much better and the tumor cell is seen easily. In this case, the tumor cell is not seen. So, the detectability of the tumor, which is here we call hepatic metastasis, is much better, and you can easily observe this kind of changes in the organs as when you add the MRI contrast agents. This is another way. When you apply, you want them to assemble or disassemble in a controlled manner. So, this is a image where you can see that the particles have been aligned in a certain fashion by using appropriate reagents or appropriate magnetic fields. So, they can be assembled or disassembled in a solution in a controlled way. So, if you can do that, then you can use it in real life. You can make it assemble at a part in the body, and you can make it disassemble using a trigger. The trigger may be a change in the magnetic field or a change in the pH or something like that. Since these are magnetic particles, then normally a change in the magnetic field can create the assembly or disassembly in a controlled manner. So, here you see magnetic separation is being applied, so that you can remove waste material from water. So, heavy metals are adsorbed on the magnetic particles, and they can be easily removed if you apply a magnetic field. So, say you use magnetic nanoparticles like iron oxide, and you use humic acid, which is available from natural sources, and humic acid is coated onto iron oxide nanoparticles. So, you have iron oxide nanoparticles, and on top of that you put humic acid, and then you put it in a solution which has got some pollutants. So, here rare earth ions or heavy metals are pollutants. So, like lead, bismuth, etcetera, or maybe lanthanides, and then they get coated, adsorbed on the magnetic nanoparticles. Once they get adsorbed on the magnetic nanoparticles, then you apply a magnetic field, all these particles will come to the position close to the applied magnetic field. So, say you are applying a magnet on one wall of the container, then all the particles will go to that part of the container where the magnet has been applied. So, that way you can remove some heavy metals in water using magnetic nanoparticles, and this process is called magnetic separation. So, this is another application of magnetic nanoparticles. So, this is the scheme. So, you can see that you have this solution which has got heavy metal ions, and you want to remove heavy metal ions from that. What you do is add nanoparticles which have been functionalized with something. So, this functionalized here can be humic acid which has coated the particles, and then you add them, and the heavy particles, the heavy metal ions get trapped on the surface of these particles, because it is functionalized with some carboxylate groups or something, and that carboxylate group can form chelates with these heavy metals like lanthanum or neodymium or lead, etc. Once it gets functionalized trapped on the surface of these particles, then you bring a magnet close to that. So, once you bring the magnet, all this black particle which is shown in a black color, they will come and deposit on the wall of this container, so that the water will be clean. So, this is a magnetic separation of these heavy metal ions using functionalized magnetic nanoparticles. So, this is a very important application, and with that we come to a close to today's lecture on magnetic nanoparticles, and it is also the close of this 3 lecture series on magnetic nanoparticles. What are magnetic nanoparticles, what are their applications, and how you make them, how you control their size, etc. So, typically we learned that when you decrease the size of magnetic nanoparticles, then it has a tendency to reverse its magnetization. That means, what you know in large sized particles to show ferromagnetism, when you make small sized particles, you will tend to get the opposite of ferromagnetism. That is, you will either get superparamagnetism, or you will get maybe weak antiferromagnetism. But and when you have antiferromagnetism, then you in a large particle, when you decrease the size of that antiferromagnet, you will tend to get either a lower Néel temperature, or you will get a weak ferromagnetism in that particle. And where you can use these particles, the particles which are ferromagnetic, the nanoparticles which are ferromagnetic can be injected in the body, and it can be used to generate energy inside the body locally, because the nanoparticles are very small. So, they will be in touch with only very few cells, and you can apply a magnetic field and heat the local environment around the particles, because during the hysteresis, when you increase magnetic field and decrease magnetic field, there will be a hysteresis in the magnetization, and that will create heating, and that will heat the environment around the magnetic particles, and that will destroy the cells around the magnetic particles. Since the particles will be very small, this heating effect will not be spread to other cells, and it will only heat where the particles are lodged. So, there will be local damage to the cells around the particles, and there will not be large scale damage of good cells in the remaining part of the organ. So, you can have very good localized treatment using magnetic which we call as hyperthermia, magnetic hyperthermia. Now, that is one thing. The other thing is, what we learned, that you can do very well what is called phase the contrast, like MRI contrast agents. They show up in medical imaging. There is lot of importance, because these magnetic nanoparticles can enhance the contrast, and so can show up some tissues against the background much better, or some tumor cells or cancerous cells against the background, and hence in medical imaging these kind of magnetic nanoparticles are of great importance, and there are many other applications like magnetic separation, etc. So, with that we come to an end to today's lecture, and I hope to meet you in the next lecture, where we will start our discussion on the optical properties of nanoparticles. Thank you very much.